So it's a great honor to be able to speak at the Academy today. I just published a new book called Schrödinger in Oxford. What I'm going to do today is take the opportunity to tell you about Schrödinger's great work and also about his fascinating life. And what you really have to do is just look at the dates and his career that span out what happened with Schrödinger. He was born in 1887 in Vienna, in Austria, and then in 1921 he had his first chair in Zurich, at the University of Zurich. And then in 1926 was the great year for Schrödinger, where he wrote 6 revolutionary papers, without doubt some of the greatest papers of the 20th century, in 1926 in Zurich. And that was his great work. After that, he never produced anything so important, but as we shall see, he did do things that had influence on other scientists, and that's important also. Just 1 year after he discovered and published his wave mechanics, he then went to Berlin as the successor to the great Max Planck at the University of Berlin. But after Hitler came to power in 1933, Schrödinger didn't like what was happening, and he left Berlin and came to my own college in Oxford, Magdalen College in Oxford. And that's why I wrote the book, Schrödinger in Oxford, because I managed to get a lot of original archives about his time in Oxford. Although the book is a general biography of Schrödinger and includes his whole life from start to finish. He couldn't get a permanent position in Oxford. It was there that he heard he'd won his Nobel Prize at the same time as Paul Dirac, but he couldn't get a permanent position. So in 1936, and very foolishly, he moved back to his home country of Austria, where he had a chair at the University of Graz. Now that was a very stupid thing to do, as he admitted later, but there were 2 important aspects now in Schrödinger's life with respect to this great city of Rome. Schrödinger only spent a few days in Rome, but the 2 times he did come here were very important to his career and his life. And I could almost write an article, not Schrödinger in Oxford, but Schrödinger in Rome. And the first time was when he was elected to the refounded Pontifical Academy of Science in 1936. And Schrödinger loved being elected to academies, including this one. And that was very important to him. And it was only a very small number of other eminent scientists were elected. So he came to that first refounded meeting in 1936. And that was crucial to his subsequent career, as we shall see. He then went back to Austria, and after the Anschluss, when Hitler's troops marched into Austria in March 1938, Schrödinger was in trouble because he had left Berlin, and the Nazi authorities were not very keen on Schrödinger. And as we shall see, he got into trouble with the Nazi authorities and had to leave very quickly from Austria. And the only place he could come to was Italy without a visa. So he and his wife just crossed the border and came here to Rome for the second time. He escaped here, and that was crucial also that he was able to do that. He then, when he was in Rome, had a phone call. He had no money, he had nowhere to stay. He stayed at the Vatican at the time, and he had a phone call from De Valera, President De Valera of Ireland, who asked him to come and set up a new institute in Dublin. That hadn't yet been arranged, and so Schrödinger had to go, first of all, back to Oxford, who didn't really want him again, then to Belgium for a few months, and then war was declared in September 1939, and he was by then a German citizen who was in real trouble. Because he had been in the Pontifical Academy of Sciences, de Valera enabled a letter, essentially a visa, to Schrödinger to get him out of Belgium, and he went to Dublin, and there he wrote a very important article that influenced molecular biology to the present day. He returned to Vienna in 1956 and died there in 1961. What I'm going to do today is sketch out his great achievements and his career, with a particular emphasis on his time at Oxford, because that's where I've managed to get a lot of original archives. Now, when Schrödinger was thinking about important areas in science, one of the most important experimental breakthroughs was the publication of the emission spectrum of the hydrogen atom by Rydberg and Balmer and others. They just took a gas of hydrogen, passed an electric current through it, and observed the emission spectrum and got these beautiful different colored lines in the spectrum here. Now, of course, the hydrogen atom is the simplest atom, just with an electron going round a proton. And that immediately excited many theoreticians, because it's quite a simple system, a bit like Copernicus's view of the Earth going around the sun. And there could then be a new theory for explaining these beautiful experimental results. Well, the first breakthrough, essentially, was by the great Danish physicist Niels Bohr, who in 1913 wrote a paper that was also very revolutionary in science. I was asked to write a review of his paper for the journal Science just a few years ago on 100 years of atomic theory. Now, first of all, what Bohr did, he said, well, those spectra are just described by stationary energy states. The atom only has particular energies. The electron can jump between those energy states, give off the radiation you see. Well, we're all used to that in science nowadays, not in 1913. That was a revolutionary breakthrough. And also, and this is what really excited the scientists, Niels Bohr showed that those frequencies of lines in the spectrum of the hydrogen atom could be explained just by fundamental constants, by the charge on the electron, the mass on the electron, and most significantly also Planck's constant that had come through from Max Planck. And so he was linking the spectral world to the thermodynamic world of Max Planck. But Bohr didn't come up with an equation. It worked, his ideas kind of worked for the hydrogen atom, not for the helium or atom or for any other molecules. So that things were stuck. And then this changed with this great paper, one of the great moments of the 20th century, when Schrödinger published his first paper on the hydrogen atom, and he came up with an equation that gave the energy levels of the hydrogen atom. This is the paper that he published when he was at the University of Zurich in 1926. And I've fortunately managed to get to a load of archives. This is the first page that is known where he scribbled down his equation when he was playing around with various mathematical equations for the hydrogen atom. And you can see from this, he actually has got relativistic terms that he started off playing around. And then he suddenly thought, I'll drop those out. And right at the bottom here is the first time anybody wrote down the Schrödinger equation. And that's what went into his great paper. Now, in terms of a simple formula, it has this very simple formula in its time-independent form, h psi equals E psi, where h is an operator that depends on the kinetic energy and on the potential energy, and the kinetic energy term is a second-order differential term. And the crucial thing that nobody had thought about before was this function, psi, the solution of the equation. that became known by him as an orbital. Well, all chemists use orbitals all the time. The orbital was invented in this paper by Schrödinger. And that gives you all the properties of the system, and E gives you the energies of the system. It was a really simple equation, and he was the first one to think of it. And not only did it give energy levels, it gave properties. And in his notebooks, which I've been through, there are pages and pages of mathematical derivation of what happened when you turn an electric field onto the hydrogen atom and look at its spectrum. And it's been shown by Stark that that splits the lines. And Schrödinger, and this is from his notebook that I have access to, gave these different splittings of lines with intensities here. And these are the experimental intensities here, and they agreed perfectly. And this really got people excited. Even the competitors of Schrödinger, Heisenberg, and even Pauli, who were always very critical of other people's work, both wrote down that this was really interesting. And the great scientists of the day, Albert Einstein, for example, said, "The idea of your article shows real genius." Max Born, who was from Göttingen, the supervisor of Heisenberg, Pauli, and Fermi, said, "We were taken by surprise by Schrödinger's wave mechanics. It quickly became the standard theory." And then the chemists jumped onto this. Linus Pauling and others realized, and this is the most important thing for chemistry and material science, that Schrödinger's equation not only worked for the hydrogen atom, they discovered it worked for the helium atom, for the hydrogen molecule, and in principle for any system of atoms or molecules, on which everything depends. Now, you could only analytically solve with mathematical formulae the Schrödinger's equation, essentially for the hydrogen atom. But as time has gone on with computers, it's become more and more possible and more accurate to do solutions that are really accurate of Schrödinger's equation. In that great year, he also in other papers showed that it worked for the harmonic oscillator. If you have a diatomic molecule vibrating backwards and forwards, you can calculate the energy levels for that. And they're quite well described by the harmonic oscillator energy levels that he published. And similarly, a molecule rotates, and you can calculate those rotational energies from Schrödinger's equation. And these results give you the infrared spectrum, and these results give you the microwave spectrum. And Schrödinger also came up with a time-dependent version of his equation. He put time into his equation, and so you can use it for dynamical processes like molecules colliding with others or light interacting with molecules. That all happened in his great year. Now, there's a myth about Schrödinger that derives from an old biography that was written by Walter Moore back in the 1980s, that Schrödinger was in this wonderful ski lodge in Irosa in Switzerland in Christmas of 1925. And he did go to that ski lodge, and it was there that he wrote down his equation, and there are letters that show that. Now, there's a myth that he was there with an unknown lady friend that came from this book by Walter Moore in the 1980s. Now, I managed to track down the original origin of that myth. It came from a professor, Peter Fischer, who's still alive, very senior in Germany. And he told me, and this is all in my book, that all of this was gossip. There is no actual truth that Schrödinger was with an unknown lady that inspired Schrödinger's equation. There are much gossip about Schrödinger and his personal life. And a great deal of that is not backed up by evidence, and that is discussed in my particular book. So I'm sorry to disappoint you if you've heard that story before, but I don't think there's evidence for it. And now in the 21st century, Schrödinger's wave mechanics is the method for explaining the structure and properties of all molecules and materials. In a subject of my own, like chemistry, every single observable can be calculated from some form of Schrödinger's equation, And if you do those calculations very accurately, you get essentially the right answer. It's an incredibly powerful theory, and as computers and algorithms come on, it's become more important. It's even used for biological molecules nowadays, for structures of proteins and materials, or even in drug discovery. When molecules interact with biological molecules, you can calculate the energy of that nowadays. And there are now drugs that people are out in clinical trials which were first predicted from solutions of Schrödinger's equation. And then the whole field of microelectronics that has revolutionized the world through semiconductors, integrated circuits, computers, mobile phones, and so on, all depends on energy levels in special materials, in semiconductors, insulators, metals, and so on. And the energy levels in all those systems are calculated with Schrödinger's wave mechanics. So it's the heart theory of modern microelectronics, if you like, which has so revolutionized the modern world. And in my own field is chemical reactions, as is true with Enzo Aquilenti's work, chemical reactions. In chemical reactions, you have a hydrogen atom or can react with another molecule like ethane and going to the products. And that hydrogen atom can tunnel through the barrier in the potential to the reaction. And this is a quantum mechanical effect. You only get it by solving Schrödinger's equation. You don't get it from classical mechanics. And it can have a huge effect on rates of chemical reactions. So this is a plot of the log plot of the rate constant for this reaction of hydrogen with ethane. Temperature along here between 200 and 500 degrees Kelvin. This line is what you get with solving Schrödinger's equation. And this is what you get with Newton's classical mechanics. And this is a log plot. So in room temperature range, there are 2 orders of magnitude difference between Schrödinger's work, which fits very nicely with experiment, as it should do, and classical mechanics. So what a theory that Schrödinger developed. Now, what I'm going to do in the remainder part of the talk is tell you some interesting things about his life, because he had a very interesting life. This was the 1920s, the 1930s, and the 1940s, which, as you know, was a quite extraordinary time in Europe. In 1933, in the spring of 1933, this professor, Frederick Lindemann, from my own university in Oxford, he was a physics professor in Oxford, went to Berlin because he realized he could recruit some scientists who were unhappy with what was happening in the Hitler regime. And he did that with quite a few Jewish scientists who in particular were under threat. But he also met Schrödinger on that occasion. Schrödinger, who was not Jewish, told Lindemann that he was very unhappy with what was happening in Berlin. And so Lindemann said, okay, come to Oxford. And that's why Schrödinger came to Oxford in 1933. And he came to Magdalen College, Oxford, as a fellow. And that's where I've been, until very recently, was president of Magdalen College in Oxford. This is my house here that I lived in for 15 years. And that is where Schrödinger came on the 9th of November, 1933, and was admitted as a fellow of the college using Latin phrases that are still used to the present day. And then the fellows took him into the hall of the college for a very fine dinner. At that time, when that dinner was going on, this telegram came into the telegram office in Oxford. And this is the telegram that all scientists want to receive. Because as you will see, it's from Stockholm. I think our president here has received one of these telegrams or equivalent. And it's handwritten. I don't think that's true nowadays. It's written in German. And it says that the Swedish Academy of Sciences has awarded the Nobel Prize, and this was actually for 1933, to Professor Schrdinger and to Professor Paul Dirac of Cambridge. And that came into the telegraph office. Now, at that time, Schrödinger was having dinner with the fellows of Magdalen College, and the president was called to his office because there was a telephone call from the Times of London saying that Schrödinger had won the Nobel Prize. So the president called Schrödinger himself to the office and told him. And this is all described in a letter in detail that Schrödinger wrote to Max Born about how he heard. He'd won the Nobel Prize with Paul Dirac in 1933. Heisenberg was also given the Nobel Prize for the year before of 1932. And this is Schrödinger just outside my office. You can see he's very pleased. He's wearing the Oxford gear, a mortar board and gown. And they have a tradition when there's a fellow is admitted that they always weigh the fellow and put their weight in a book. And this is the book. It says November the 9th, 1933, E. Schrödinger, 10 stone, 9 pounds. He was actually weighed on 4 other occasions, and his weight never changed in that time, in the 1930s. So then the next day, November the 10th, what did the newspapers say? So this is the Times of London. The headline, Herr Hitler at Munich, a Nazi festival. The Reichstag trial, and the Nobel Prize in physics. And it says, Paul Dirac of Cambridge and Professor Erwin Schrödinger of Magdalen College, Oxford. He'd only been in Magdalen College, Oxford for 1 day. Yet, fair enough, he'd left Berlin and he'd been made a fellow, so it was claimed by Magdalen College, Oxford. And the newspaper then described it almost as a competition between Oxford and Cambridge. And you get similar reports in other newspapers all around the world. This is one I found for this talk from Italy, La Stampa, of the same date, November the 10th, 1933. And on its front page, it had the Nobel Prize in physics, as you can see. And if you go down a little bit, it does mention the one to Werner Heisenberg, but it also says Professor Schrödinger of Oxford. So even in the other newspapers in this country were saying the same thing, that Schrödinger had won his Nobel Prize in Oxford. And one of the nice things about the Nobel Prize is if you win it with somebody else, you become great friends with that person. And so this was a very nice letter that Paul Dirac wrote to Schrödinger just after the announcement. Dirac won the prize essentially for his wonderful theory of quantum mechanics that followed on from Schrödinger's wave mechanics, but also predicted the positron, the particle of the positron. And there's a wonderful film of Dirac in this room giving a lecture about the positron that you can find on the web. And this is a lovely letter, I think. Many thanks for your kind letter and congratulations, says Dirac to Schrödinger. May I congratulate you? I'm very glad indeed to be in the company of you and Heisenberg, and hope we shall have a good time together in Stockholm. Now, any of you who know about Dirac, he's the last person you're going to have a good time together. He was the most introverted, complicated scientist. You couldn't imagine having a really good time with Paul Dirac. And then this is I said about the great paper of the 20th century. In my view, this is one of the great photographs of the 20th century, because it is Dirac, Heisenberg, and Schrödinger who all arrived on December the 9th to get their Nobel Prizes in Stockholm. The ladies, the middle lady is Annie, the long-suffering wife of Schrödinger, and the other two were the mothers of Dirac and Heisenberg, who neither were married at that time. In fact, Dirac, as he famously used to say, married Wigner's sister. Anyway, that is and it shows you the sort of character, the very thoughtful Dirac, and very intelligent Heisenberg, and the flamboyant Schrödinger, who's wearing a rather flamboyant gear when he went to Stockholm to receive his prize from the King of Sweden. Now, Schrödinger then went back to Oxford because he had a position at Fellow at Magdalen College, and then he received some interesting letters. And I was lucky to visit Schrödinger's daughter in Austria. She died a few years ago, but before that, we visited her, and she gave me access to some of her precious archives. This is one that's not published before, but it's in my book. This was a letter that Schrödinger received in 1935. According to your request, I relieve you with effect from the end of March of your official obligations in the philosophy faculty of the University of Berlin. I express my thanks to you for your academic achievements and for the services you have performed for the state. Der Führer and Reichskanzler Adolf Hitler. Because all the appointments to professorships in a university such as the University of Berlin and other universities had to be approved by the Chancellor of Germany, and when people resigned, he sent a resignation letter. So you must admit this is quite historic document, and one of the only nice letters I think that Adolf Hitler ever wrote. Now, when Schrödinger was in Oxford, he wrote two papers that were really influential, and this one, in some ways scientifically, the most influential, and it's on the probability relations between separated systems. It's in English. It was communicated by his great friend Max Born to the Cambridge Philosophical Society in 1935. And it's a very simple paper. And what Schrödinger says is if you have two systems, two quantum systems, they could be two atoms or two electrons, they can interact with each other. And even if they're at some distance away, they can interact with each other. And they can become entangled in their language of quantum mechanics. And this is, on this abstract, he says, by the interaction, the two representatives of the wave functions have become entangled. To disentangle them, we must gather further information by experiment. And that's the first time the word entangled was used in quantum mechanics. And now in modern physics, it's something you see in all different laboratories, the ideas in physics of systems becoming entangled and how to do experiments to observe the mixing between the different states. And the Nobel Prize, just for the last Nobel Prize in 2022, went exactly to that field for new experiments on entanglement by Aspet, Clauser, and Zellinger. And it's really good, and people don't know that Schrödinger submitted this paper from Oxford in 1935. And this is the paper that really started off the whole modern physics field of entanglement. Now, there's another paper he wrote from Oxford in the same year, which has become very famous to the public. And that is his Schrödinger cat paper. This is in German. He submitted it to the Naturwissenschaften, the journal that was edited by his great friend Arnold Berliner, who was in a lot of trouble with the Nazis at the time, and he wanted to help his friend Arnold Berliner, so he didn't do this to an English journal. It went to a German journal. But what I like is it says von E. Schrödinger, Oxford. It doesn't give his full address like you do nowadays, but that was good enough in those days. And this was the Schrödinger cat. He did mention, this is from his paper Ein Katz, in which he came up with what he called was a ridiculous thought experiment. He tried to show that some of the ideas of probability in quantum mechanics that had come actually from Max Born were absurd. He tried to show that through a ridiculous thought experiment in which he had a box, he had a phial of poison gas and a bit of radioactive material and a cat. And he put a top on the box, and then the radioactive material suddenly came and broke the phial of poison gas, which could go and kill the cat. But you don't know when that's going to happen. And so Schrödinger said that if you've got the top on the box and you can't see inside the box, you don't know if the cat is alive or dead. Its wave function is a linear combination of the dead and alive cat. And because it was a cat, not because it was any other animal, it was the friendly cat, this really got into the public eye and is a phrase used in many other contexts now when two different things can happen at the same time. And this paper, it's not a great scientific paper, but it got quantum mechanics into the public eye, and we've seen that Schrödinger is good at doing that. The other problem about him in Oxford was he was almost a postdoc. He only had a 3-year appointment. He'd been promised a chair when a professor, August Love, who'd worked on wave theory, died or retired, but August Love lived throughout the 30s. And so Schrödinger didn't have the chair, and he was just had a postdoctoral position from ICI, Imperial Chemical Industries, and had to renew that every year with a report, just like a postdoc. The great Schrödinger, Nobel Prize winner. And so I got copies of these reports. This is one of them about what he'd done in the year 33 to 34. I've been engaged during this period, as in the previous 7 years, closely connected with the revolutionary change in physical theories. And that's the sort of report he had to make. And he didn't like this sort of thing. No great scientist would like having to do that. And nor did Schrödinger really like the social life in Oxford. In Oxford, there's a lot of wining and dining and activities and events. Some people like those. I quite enjoyed those events, but Schrödinger didn't really like the social life associated with it. And he told Max Born, you never know who your neighbor might be at dinner. You talk to him in your natural manner, and it turns out that he's an archbishop or general. Huh. I find, personally, I used to find that quite interesting, but for some reason, Schrödinger didn't really like it. And he was offered a chair back in Austria. So in 1936, after 3 years in Oxford, he moved back to Graz, to a chair that was available for him as a professor at Graz and also an honorary professor at his old university, the University of Vienna. This was his biggest mistake, because he moved back in September 1936, and the political situation in Austria was very bad and getting worse. And the Anschluss came in March 1938, when Schrödinger was still in Austria, and the Germans troops had marched in during that time, and then he was in big trouble. And so Professor Lindemann and Professor George Gordon, who was president of Magdalen College, then did their very best to get Schrödinger out of Austria. They offered him a series of lectures that he could come back and give. And Lindemann and Gordon then got through to the Foreign Secretary of Great Britain, whose name was Lord Halifax, who by a coincidence was also Chancellor of the University of Oxford at that time, and persuaded Halifax to go right to the top in Germany to see if they could fish Schrödinger out of Austria, and so he could come back to Oxford. And this was the letter that the Foreign Secretary wrote about this to Lindemann. With reference to your telephone message, I'm writing to let you know that our ambassador in Berlin has now had a reply from the German Minister for Foreign Affairs to the inquiries he made at my request about Professor Schrödinger. I'm sorry to have to tell you that Herr Ribbentrop's reply is unfavorable. According to the German authorities, Professor Schrödinger left Germany in 1933 for political reasons, and after a brief stay in Oxford, settled in Graz, where he proceeded to busy himself as a fanatical opponent of the new Germany and of National Socialism. So after looking at his case, Ribbentrop said, we're not going to give a permit for Schrödinger to leave Austria and go back to Oxford. And so the bells were really ringing for Schrödinger then at this time, and for many other people in Austria who had to leave at that time. So what he did, he dropped everything. He put his Nobel Prize and other prizes, medal, at the back of a filing cabinet in Graz. He left his car behind. He didn't even take any money with him. He and his wife just got on a train, and there was only one country they could come to, and that was Italy, without a visa at that time. So that's what he did. And he came to Rome. He came here to Rome. This was in September 1938, just a week before the Munich discussions between the great powers in Europe. And he arrived at the station in Rome. He had no money. He got a taxi to the Vatican. Because he had been made a member of the Pontifical Academy of Sciences in 1936, he was allowed to go and stay in the Vatican. And he couldn't even pay his taxi fares. He managed to telephone his friend Fermi in Rome, who came and paid for the taxi, and also lent him a bit more money so that he can get by. So the fact that he'd been made a member of the Pontifical Academy 2 years before, and now the help he received again from Rome, was crucial to Schrödinger in being able to escape from Austria. And when he was in the Vatican, President de Valera of Ireland, who had very good connections because Ireland is a Catholic country with the Vatican, telephoned Schrödinger and said, we'll set up a special institute for you, an institute of advanced studies in Dublin, and you can come and be the director. But it will take a little time. And he managed to get Schrödinger with a letter then to come back to Oxford. Late in 1938, Schrödinger had nowhere to live, he had no money, he had to give a few lectures again just to make a little bit of money. He even went and stayed for a couple of weeks with his friend Paul Dirac in Cambridge, and then was given a 6-month appointment in Belgium. So he went to Belgium. And in Belgium, in Ghent in Belgium, he had a position for a few months, and then war was declared in September, and then de Valera managed to get him out of Belgium, and he went to Ireland. And he stayed there from 1939 right up until 1955. And that turned out to be a very good place to spend the Second World War at the end of the day. With all the trouble occurring everywhere else, things were peaceful in Ireland. And then after the war, several academies became interested in Schrödinger, and the Academy heard it. He was elected into the Accademia dei Lincei in 1947 at the same time as Heisenberg, as a member of this academy. And your academy did better than the Royal Society, because in 1945, Paul Dirac nominated at the same time Schrödinger and Heisenberg to become foreign members of the Royal Society, and there was not strong support for them. Schrödinger had this complicated personal life, and I'll say a little bit more about that later. And Heisenberg had been involved in the war with the nuclear research, which had various question marks against it. So neither Schrödinger or Heisenberg were picked up by the Royal Society until 1949, when Schrödinger was elected, and Heisenberg it took till 1955 till he was elected. So your academy did much better than the Royal Society. And I wrote a very detailed article on this with lots of letters from all the fellows of the Royal Society and others trying to get Schrödinger and Heisenberg elected. In the end, they were successful, but they didn't do as well as your academy here. Now, while Schrödinger was in Ireland, this was in 1943, he wrote a little book on a totally different topic, and it was called What is Life? And what he did in that book, he essentially said that you can use the basic principles of physics and chemistry to explain biology and molecular biology. Now, he had a few ideas in that little book that weren't quite right. For example, he only mentioned entropy and not free energy. And there are various other sort of scientific mistakes. But the basic idea that you can use the fundamentals of physics and chemistry to explain biology was novel, and it caught the idea of many of the modern people in molecular biology. In their own biographies, both Francis Crick, James Watson and Maurice Wilkins, who all together won the Nobel Prize for understanding how important the structure of DNA was, they all wrote that it was Schrödinger's little book that converted them from being physicists to go and work on molecular biology. So we've seen, as we see nowadays actually with Schrödinger's idea on entanglement, he was very influential on other scientists. He was a great pioneer in communicating science beyond the particular discipline he was in. He was a very good lecturer and speaker. And so this was a highly influential work, not great science, but highly influential in getting other people the foundation paper, essentially, of the whole field of molecular biology. He then eventually returned in 1956 to Austria. They found him, he came back as a hero. They found him a chair at the old University of Vienna. All was forgiven. When he went back to Austria, he went to Graz and found the filing cabinet where he put his gold Nobel Prize medal. And this story was told to me by his daughter. And the front of the filing cabinet had all been smashed in by Russian troops, but they'd left the back of it. He went to the back, and his medal was still there, as were some of his precious manuscripts, and I've shown you one or two of those. This is his gravestone, which is in Outback in Austria, a beautiful place, which has, he died in 1961, and also with his long-suffering wife, Annie, and on his gravestone is the time-dependent Schrödinger equation. And Austria put his face on the stamps. His face hasn't come on the euro yet, but they had it on the Austrian shilling. And in 1923, Schrödinger's wave mechanics forms the basis for essentially the whole of chemistry. He invented the orbital. He invented the way to calculate all experimental observables in chemistry. Bond energies, spectra, molecular structure, reaction rates, all come from Schrödinger's equation. And if you can solve it accurately, you get the right answer. But not just in chemistry, in many areas of physics, but particularly in condensed matter physics, for example, where he's been so influential, and also in material science, and increasingly in not just his influence in molecular biology, but people in biology are starting to solve Schrödinger's equation in that particular field. And finally, I just want to say my own little contribution to this story. Schrödinger had an illegitimate daughter, Ruth, who was born in Oxford in 1933. Schrödinger had a postdoc, Arthur March, who came with him to Oxford and who was married, and his wife was pregnant, and she had the baby in Oxford in 1933. Now, it turns out, and this is Ruth with Schrödinger. She followed him all these different places over Europe and ended up being educated in Dublin, in Ireland. This is Ruth playing chess with Schrödinger. And Ruth told myself and my wife, Heather, who's here today, that she was sitting by a lake when she was age 17, when Schrödinger had gone after the war. Schrödinger was back in Austria for a short period and was looking at their feet. And Schrödinger said to Ruth, "Your feet look just like mine." And she said, "Oh, yes." And Schrödinger said, "Well, I have to tell you the reason for that. I'm your father." And she hadn't known that till the age of 17. That's Ruth. This is his great friend, Max Born. Max Born won the Nobel Prize in, I think, 1954 for his interpretation of Schrödinger's wave function in terms of the probability idea. An idea that Einstein didn't agree with, an idea that Schrödinger didn't agree with, but just about all other scientists agree with it. But he was always a great friend of Schrödinger, and this is Max Born with his son, Gustav, who was born in Germany. Now, Ruth followed Schrödinger. She was born in Oxford. She was in Austria. She even was in Belgium with Schrödinger, and then Dublin. And Gustav followed his father, Max Born, who also left Germany in 1933. He was Jewish. He came from the great University of Göttingen. And went to Cambridge, where he also only had a temporary position for 3 years before being a professor at the University of Edinburgh. And there's Gustav, his son. And these two were refugees in Europe, and they never met each other until 27th of April, 2008, when I had a special event for the 550th anniversary of Magdalen College, when we celebrated our 9 Nobel Prize winners and had talks on those Nobel Prize winners and on Schrödinger. And this was the very second when Ruth Braunitzer, the daughter of Schrödinger, who's there, and Gustav Born, the son of Born, this is the very second that they first met. And I'm proud to be in the middle of this story. And those two very fine people, they passed away a few years ago, but they gave me very helpful information for my book on Schrödinger in Oxford. Now, Schrödinger had a complicated private life. We've heard he had an illegitimate daughter, Ruth. It's known he had 2 other illegitimate children with other women, and he did not have a private life to be proud of. Now, there are other stories about Schrödinger's private life which are much worse than that. And I've looked into the evidence for that, and those others are just stories and gossip. There is no evidence for it. In my mind, he did not have a private life to be proud of, but he wasn't worse than that. He was summed up here by his friend Max Born. Schrödinger's private life seems strange to bourgeois people like ourselves, but all of this did not matter. He was a most lovable person, independent, amusing, temperamental, kind, and generous, and he had a most perfect and efficient brain. And if you're interested, this is the book that describes all of this story. Thank you for your attention.